All right, we are back, finishing up. Well, not finishing up. We are back, sort of resetting and restarting with abstract algebra. We were, before spring break, we left off in chapter 6, right, which consisted of discussing isomorphisms. And what I would suggest you do is pause the video and write everything down, and then I'll go back over it and go over it. So really, might be helpful, because we're going to use this new format and see how this works. It may be helpful to, like I said, pause the video, write your notes, and then annotate as I go back. So when I go back over what I'm doing, if there's something that you might need to add to clarify, then annotate your notes. These are your notes, and however you need to understand something, that's what you should do. All right, so we left off with Cayley's theorem, and which says what? Every group is isomorphic to a group of permutations, right? So that was the big theorem, and we proved that before spring break. And then we talked about, so you may have this already. I wasn't for sure, so I just said I'll go back over it. So you may have this in your notes. If you do, you can just follow along until we get to the new part in your notes. I think you have the second part. I don't know if I wrote this on the board. So the importance of Cayley's theorem is that it's used to represent an abstract group in a concrete way. And again, that theorem is important because any group we can think of, it's going to be isomorphic to a group of permutations. And in regards to a group of permutations, we're familiar with their structure and how they operate. And so that's why we can take some abstract group and represent it in a concrete way, because we can ideally convert it to a group of permutations, because isomorphic means that it's the same form, right? We talked about that. Okay, so that's the importance of Cayley's theorem, the first part. The second part, in terms of the importance of Cayley's theorem, is that abstract groups are the same as permutation groups, and permutation groups are viewed throughout other branches of mathematics. And so I think someone in class who's taking like a combinatorics or discussing combinatorics, maybe even linear algebra 2, I think some people talked about. So just in other fields where permutation groups are discussed, we can think about abstract groups. Okay, so we went over, I do remember we wrote down the notes about the properties of isomorphism acting on an element. Now, in regards to acting on a group, suppose that phi, all right, is an isomorphism from a group G onto a group G prime, all right? So in terms of groups, we have the following properties. And again, you may have this already. One, phi inverse is an isomorphism from G prime to G, right? Because when we talk about inverses, they flip our domain and range. 2, G is abelian if and only if G prime is abelian. And we're not really, because of time, but maybe during problem solving or during office hours, if you have questions, I want you to try to prove these. All right. So this is something that you should be able to prove using what we know about isomorphisms and groups. Okay. So number 2, G is abelian if and only if G prime is abelian. Number 3, G is cyclic if and only if G prime is cyclic. 4, if K is a subgroup of G, okay, if K is a subgroup of G, then phi of K equals the set phi little k, okay, where K belongs to big K, that is a subgroup of G prime. All right, so this is just talking about codomain range type of thing. 5, if K prime is a subgroup of G prime, so now we're talking about our codomain, then phi inverse of K prime is a subgroup of G, okay? And I think did I want to do a diagram? Let's see. Okay, and for 4 or 5, we can take those and look at them with Venn diagrams to make sure. So 4, we think visually what this is saying. So we have G. So we have G, phi to G prime. Sorry for my scribble on here. I'm trying not to make it too big. All right, so this is saying if K is a subgroup of G. All right, so K is a subgroup of G. Then phi of K, which where all the values in K in our domain will be mapped to, that's also going to be a subgroup of G prime. Okay, and then for the other one, in regards to number 5, I'll put it here. So again, if we're looking at G and G prime, and this time we're starting off in the codomain. So now we're saying if K prime is here, right, then the inverse image, right, that term may be familiar from foundations, proofwriting. Inverse image of K prime, okay, sort of working backwards, right, is a subgroup of G. Okay, so that's sort of visually what that's saying. And like I said, these should be easy properties to prove. And then the last one, phi of Z of G equals Z of G prime. Okay, so again, you might want to pause the video. But here, note that these properties help us conclude when two groups are not isomorphic. And I think I wrote this down too. So I think some of you were absent before spring break, so this might be new to you, but if not, we'll just go over it again. Thus, we know that G and G prime are not isomorphic if, well, of course, if we're talking about isomorphisms, then the cardinalities have to be the same, right? So the order of G does not equal the order of G prime. So if that's the case, we automatically know they cannot be isomorphic groups. If G or G prime, so that's number 1. Number 2, if G or G prime is cyclic, but the other's not, right? And these are just coming from the properties we know. 3, if G or G prime is abelian, then the other is not. 4, if we can show that the largest order in G is not equal to the largest order in G prime, because again, and I feel like I've been drilling it into your head, but whenever you hear the word isomorphism, or whenever you think or hear that two things are isomorphic to each other, that's telling you that whatever I see over here in terms of structures, I'm seeing over there. The notation may be different, right? And again, just like if I say Je m'appelle Dr. Brown in French, then in English that's saying my name is Dr. Brown, right? So those two are isomorphic statements. 5, if you show that the smallest number of elements of some order in G is greater than 1. Oh, no, I'm sorry. I'm looking at how I wrote these notes. If you show that the smallest number of elements of some order in G, the smallest number greater than 1 is usually a good choice. It is not the same as the number of elements of that order in G. Okay, and so looking at example 6 here, consider the groups of order 12, Z12, D6, A4. The largest order of any element in the 3 groups are what? Well, Z12, that largest order will be 12. D6, that largest order is 6. And A4, it's 3. And you can check that on your own. Thus, no two groups are isomorphic. Also, the number of elements of order 2 in each are 1, 7, and 3 respectively. Okay, so again, it has to have whatever properties hold in one group, it has to hold in the other. I think this would be a nice place to stop. I'm going to do another video talking about automorphism next.